Hey, hi everyone, this is Vivek, and in this people's choice problem, we're gonna play this game single line. So let's get started. So I'm gonna start with the first level, and we have to just take the dots and then draw the diagram in a single draw, right? So that's what we are kind of taking over here, and we gotta add. So this is like one of the problems that was suggested to me on the community question, and that's why we are playing this particular game. So we just have to draw the whole diagram in a single flow. I mean, it's like you draw it with one draw, right? Let's play a few more levels. So in this case, I can start over here and then maybe draw this and then start end over here, right? And then let's say we have this particular diagram. So I start over here and then maybe draw this up in this way, and it's drawn, right? Every line is drawn exactly once. In this case, I can start over here and then I can draw this way, right? So this is the game that we are kind of playing today. And I can start over here and then I can maybe draw this up this way, right? Let's take one more. This is going to be the final one. I don't want to take more than this. So right, this is what we are solving. But now you're saying that, Vivek, how are you solving this particular game so fast? What is the logic for this? That's what we're going to take up today. And in fact, the suggested problem that was given to me today was this CACS problem, mail delivery, which is what we are solving today. That given that you are given as inhabitants of a city, for this reason you want to find a route says whose starting and ending points are post office, are a given node. It's a fixed post office, and then it goes through every street exactly once. And this game is a bit different. In this case, we can start anywhere and end anywhere, and then we have to just find out, is there a possible thing or not, right? So this is exactly there, and this particular route where every street is uh, covered exactly once, and you have to start and end at the post office, which is the node number one, by the way, is called Euler tour of the graph. So the question is, we have to find a Euler tour of a graph. And in this particular game that we were playing, in this case, we were given that this kind of a diagram, we have to find an Eulerian path of this. So we started over here, but we are ending over here. So we have to find a Eulerian path in this, right? So let's see how do we solve these kind of problems with us in a very, very fast manner. So in fact, this is a quick screenshot of the question that somebody, Keshav, suggested that we should take this particular problem this week. And in people's choice, we are taking CACS mail delivery, right? Let's go into the problem. So in this particular problem, we have to find a particular maybe this. Okay. So let's say this particular graph is given to us, and we have to trace this particular graph. And if I have to draw it, I can quickly do this, right? I can solve it very quick. But how did I know where to start, which edge to take, and so on? Like, how am I solving this very fast? There is a very simple rule for this, that how does the condition, like how does the path exist and how to find it out, right? So the rule that I'm following virtually in my mind is, number one, for the path to exist, there are certain conditions. Obviously, there should be one component of edges. I mean to say, every edge should be reachable from in the same part, right? I mean, if we have a single node, it's still fine. It depends on the definition of the problem, but in this case, we have to just find a path which has every edge exactly once. So isolated nodes are no problem. And the thing is, if there is an edge over here, if you start in this component, you can never reach this component, and so on, and vice versa. So there should be one component exactly. Okay. The second condition that exists for finding Eulerian path in a graph is number of odd degree nodes can be equal to either 0 or equal to 2. Okay. If the number of odd degree nodes are 0 or 2, then only there is an Eulerian path possible. And so in these two cases, you have Euler path, which means you can start anywhere, end anywhere, and you can trace the whole graph. Okay. And the second condition in this case would lie is, if you want Euler tour, okay, which means you start and end at the same point, it has to be exactly equal to 0. It cannot be 2. Okay. Now this is the two condition for existence of Eulerian path or Eulerian cycle, Eulerian tour in the graph. And the way to find it is actually an algorithm. So there are two algorithms. Number one, something called as Fleury's algorithm. Fleury's algorithm. The second one is Hierholzer's algorithm. I forgot the spelling, but Holzer's, I hope that's right. Hierholzer's algorithm. So there are two algorithms which are predominantly used to find the like Eulerian paths. But we're gonna use this in code. But while like mentally solving, we're gonna have the rule for Fleury's algorithm in mind. So let's see what these are. First of all, where to start is what we have to decide, right? So when we have, let's find out the number of odd degree nodes. This is number 1, number 2, and then rest all of them are even degree, right? So there are 2. So we are in this condition. So this has a Eulerian path, okay? And it's all one component also. So the rule is to start when you have 2 and you want to find Eulerian path, start at one of the 2 nodes which has odd degree. That's what in fact I was doing when I was solving the game. So I start over here, and then the Fleury's algorithm says is when you are taking an edge, never burn a bridge and you will find an Eulerian path. So see, right now if I go through this edge is not a bridge, right? So I can take it. I can take this edge because it's not a bridge. I can take this edge because it's not a bridge. I can take this. So let's do it a bit different way. I can take this edge because it's not a bridge. I can so in this case we don't really get a condition where we're getting a bridge, but like we can take this because it's not a bridge, it's not a bridge, it's not a bridge, it's not a bridge, right? So let's make one more kind of an setup. Okay, let's make one more graph. So over here we go to this, something like this. So let's say we will simply start and count the number of nodes with odd and even degree. So this is odd, or even, odd, even. So these are the 2 starting and ending points. So I can start over here, trace this. This is not a bridge, not a bridge. But now if you see, there are 2 options. I can take this, I can take this, I can take this. But if I take this, right? If I take this, I can never take this edge again. And now you have 2 different components. These edges are not explored, right? And you are now in this particular part and you can never come back. So this was a bridge. So Fleury's algorithm says never burn a bridge and you will find an Eulerian path. So essentially the better way was to follow this one. So we should have gone this, and then go down this way. So we would get an Eulerian path. So the mentally when I'm solving that in a game, I'm thinking about fine, don't use a bridge when you are kind of finding an edge. Anything else will give you a Eulerian path. That's the mental algorithm. But while solving in code, we will have this Hierholzer's algorithm, which is very, very nice. The reason why we switch from this to this is finding a bridge takes us order v plus e, and then we will have to make the whole path. So it will take us order e times v plus e, something like this kind of a complexity. If you do it naively, we might optimize it a bit, but it's a squarish e square v square algorithm kind of, right? Hierholzer's algorithm on the other hand is actually order v plus e, which is the best thing about it, and which makes it very easy to code. Okay, so Hierholzer's algorithm says that it's a modification to DFS, right? So let's go back to this. Let's maybe create a new graph and then see if we can simulate Hierholzer's algorithm on that, right? So Hierholzer's algorithm says that we will write a DFS in this way, DFS, okay, for a particular node X. There is no need to visit anything or mark anything as visited in the DFS. What we will do is for every neighbor, for v in g of x, the neighbor of x, right, we will delete, like if this edge is like not visited because it's present in the graph. In this Hierholzer's algorithm, we modify the graph. So we delete the node g of, we will delete the node, delete the edge between the vertex v and e. If you are at from x to v, you're going to v to x, and then you will do DFS at v. Note that in this case we don't need to mark a visited because since the edge is getting deleted, so we cannot come back from v to x, so that's not a problem. And then after that you just simply append. So there is a global path that you keep, and then path dot append, like path dot pushback. You simply put the node x over here, and just simply running this whole altogether in the graph gives you a Eulerian path in the graph. provided you start the DFS at the correct one of the two endpoints and then run it. Okay, so this is the whole idea, that you start the DFS at one of the nodes and simply let the whole this particular code flow, right, and delete the edges and handle it in any particular way, and then the rest will be solved. But how does this work? I mean, this looks very mysterious. Before that, how will we delete an edge in the graph? So if you are using an adjacency matrix, we can flip off some of the bits. But if you're using adjacency list, the way we do that is we have to delete the edge between the two, and in list you cannot delete from the middle. We generally store it in vectors and we cannot delete. So we can keep vector of sets in the graph and then delete it using that. Okay, so that is the easiest way to do this. Maybe there are some ways in which you can handle the edges being deleted in between as well. There is actually a way to do that, but we don't want to go into that kind of complexity altogether, so no need to go into that. So we delete the edge between the two, and then simply continue. So this is the whole idea, and we will keep it as simple as it can be. We don't want to make it complicated and then maybe later on forget it. Keep it simple and remember it for a longer time. The way it works is, it will find this edge and it will delete it. It will find this edge and it will delete it. It will go to this node and it will delete this edge. It will go this way, this way, this way, this way, this way, and then when it track backs, it will push back everything into the whole path, right? So in this case, it's all a single path, so all of the things will come up in the Eulerian path. Let's take a different graph, and that will make more idea on how does things work. Let's see. Let's take this graph. Okay, so let's see. Let's take this one. So we have this path array over here, right? We have this path array, and we don't wanna like start over here. So we start from this node. Like, this is one of the odd nodes. The other odd node is over here. Rest everything is even. So we will go over this place in DFS, and then we will burn this off. We'll go into this, we will burn this off. We go into this, we burn this off, and then we go into this, we burn this off, and see that for this node, every other edge that is there to this is burned. So it's like an end to the DFS, and then we will push back this node. Okay, so let's number this 1, 2, 3, 4, 5, 6, right? So we will get 2 into the whole path, and then it will track back from this, right, in the recursion. But this is already deleted, so the only edge left is these two. So it will go into this, it will go into this, it will go into this, and then now see that everything is deleted. So it will push back 4, and then it will come back, and then it will come into this 5, 6, 4, right? It's 5, 6, and then 4, and then it returns back into this, then 3, 2, 1. That's how it will work, and this is actually a Eulerian path, right? This is, you can reverse it to get the way, like get the path that started from the same node if you want to get that. The reason this works is it kind of decomposes into different nodes. So you can see that this 4 to 4 over here, like like you went from this, right? So this is like a circuit altogether. So this is a circuit altogether, wherein this 4 expands into another cycle, right? So this 4 to 4 is like one cycle, right, which we found out in a separate DFS, and then 3 to 1 was the main like chain, that was the Eulerian path. So what Hierholzer's algorithm does is, in the DFS while you are deleting, it finds out the first path, one of the paths, and then whenever it bifurcates into a different DFS in a separate part, it explores different cycles. So it finds out the main chain, and then for every node it kind of expands it into a cycle and then expands that chain. And then maybe it might so have been that there was a new thing over here, so this 5 would expand into, let's say, 8, 7, 8. It might so be that 5 will expand into 5, 7, 8, 5, something like this. So it will be the new Euler tour that you have. So this is how Hierholzer's algorithm works. It kind of brings the chain and then expands the cycle in top of it, if you have to think it intuitively. But essentially this simple code that we have written over here will do the trick, right? So this is how Hierholzer's algorithm works, and this is how you find Euler tours in graph. Now this is something that we can actually use to solve the main game that we were playing. So let's continue playing a few more levels. I mean, now since you know the rule, let's see if you can apply that and actually solve the levels in the game. So over here we were having this game. Let's move into the next level. So over here we find out the number of nodes which have odd degree. This node looks like an odd, this looks like an odd. So we have to start over here. We don't burn any bridge, right? This is just simple. Now if you know the rule, you know where to start, and you just simply keep playing, right? Similarly over here, you can in this case we have to find an Eulerian tour. So let's go back. We found out where to start when we have 2, where to start when we have a 0, and it turns out it doesn't really matter, you can start anywhere. In the problem you were given that you have to start at the post office, which was at node number 1, so just simply use the same algorithm, right, and call the DFS at 1. You will get the path from starting from 1 to 1. Okay. Why does this work? So essentially the idea for Eulerian path and Eulerian tour is, like, let's say this was an Eulerian path starting from this to this, right? If you had this one more edge, it's like an Eulerian tour, right? You had this path and then this was an extra thing. So this is not present. That's why, like, if you have a path, you can add one more edge and make it a tour. And that's why 2 is allowed, because adding one edge will change both of those odd into an even, and you have 0 altogether. So in that case, you have an Eulerian tour. So this is how you can think about it also. So this is how you handle undirected cases of Eulerian tour, which was given in the problem, by the way. Right, in the problem you were given an undirected graph, and this is how you handle it. Now I will leave for you to think about how do you actually find out if it's a directed case, right? Just simply Google this up. How do you find Eulerian paths in case of directed case? The conditions change a slightly. Okay, if you have the Eulerian, so now like every node has some incoming nodes, some incoming edges, outgoing edges, right? So if you think about it in terms of Eulerian graph, like if a node is some intermediate node, the number of in degree should be equal to out degree, right? And if it is some starting node, then it has one extra out degree, right? And if it's an ending node, then it's an Eulerian path, then it's an extra one in degree, and then rest all is like paired up. Something comes in and something goes out. So that's how you find out the starting and ending nodes. One with extra one node, one extra out degree, one extra in degree are the starting and ending nodes, and everything else should be exactly balanced. In that case, you have an Eulerian path, and the way to find that is exactly same. Is just that you handle these codes with a directed case in a directed case. That's it. That's the directed case. So you can practice that also, but for this problem that we had, this is the main idea. Go ahead and code this up using a vector of set, and then maybe you can think about how do you actually make it purely v plus e, because if you have vector of set, you are essentially deleting something and there is a log factor. Can we make it v plus e? I will leave that for you. Okay, but now at least I don't know if you're gonna solve this problem or not in the CACS. I think you should if you're watching this particular video, but at least you can now play these games in any particular mobile and get a high score real quick, because this is 3 degree, so I can simply quickly just connect these things and you're done with the game, right? So now I don't know if you solve this problem or not, but you are actually like champion of a particular game, right? So that's all for this particular video. I hope you like this, and we will do more such things. Do suggest me more such problems in the comments. I will take more such people's choice problem in my videos, and we will try to solve more such things. In fact, the graph section of this whole CACS is really interesting, so take out problems that you feel interesting out of this or somewhere else as well, and we will discuss that. Okay, that's all for this particular video. Do like the video and subscribe to the channel. Please don't forget that, because that helps me to make these contents even more interesting and more at a more higher pace, and we will meet up in the next video where we discuss more such problems, right? So that's all. Do subscribe, I mean, if you have not. See you. Bye bye.